I want to show you one other integral application with parametrics that I've seen on a lot of free response AP questions. It's really common. I actually pulled this from a practice AP test that was a free response question. It was part of an overall bigger question. And with this, it's going to ask you to find the position of a particle. So it's still back to particle motion with a lot of given information. So here's what they're giving you with this. They're giving you the derivative already. So they're kind of starting out with the derivative of x, dx dt, and the derivative of y. And they also give you an initial piece of information. They tell you that at time 0, that your position is 2, -3, and the goal is to find the position at 2. So you're going to have to treat this basically like two separate problems. You're going to have to completely look at the x piece, the dx dt, and then completely look at the y piece. So here's what I know. I know that if I integrate my x dx dt, so if I integrate t squared plus 7t, I know I'm going to get the original x value, which will be my position of x. So I'm going to take what I know and what I need and make that be my boundaries. I know the x position at 0. I know it's 2. I don't know the x position at 2. So I'm going to set up my integral, my definite integral like that. That's going to give me my position at 2 minus the position at 0. This is a fundamental theorem of calculus. The idea that you do when you integrate, you get top minus bottom. So my top boundary is 2 and my bottom boundary is 0. Here's where having a calculator makes it so much easier. If you didn't have a calculator, you would actually have to integrate this by hand, have a plus c when you're done integrating, and then use your initial information to find c, and then go back and find the position. But a calculator is going to really streamline that process. So you're going to go to your calculator, you're going to do math 9, and you're going to evaluate this definite integral. So 0 to 2, t squared plus 7t. And that's going to give you 16.6 repeated. I'm just going to write it like that. We know x of 2 is what I'm looking for. We know x of 0 is 2 because that is your x value when t is 0. So I'm going to add 2 to both sides. So I'm going to add 2. I'm going to write it as a fraction just because we tend to work with fractions more often. And we get 56/3. So that's my x position at 2. That's half the problem. That gives you the x piece. Now we're going to do the exact same thing, but use the y information. So now I have my y derivative, which is the sine of 4t plus t cubed. This one, you're really happy you have a calculator because that's no fun to go through and integrate. And same thing, I know what happens at 0. I want to know what happens at 2. So those are my boundaries. When I integrate that, I would get the y position at 2 minus the y position at 0. Go to the calculator, make sure you're in radian mode because it actually matters now with a trig function. So math 9, 0 to 2, sine of 4t plus t to the third. That's going to evaluate the integral. I get 4.286. I'm just going to write the first so many digits, but I'm not going to round it. Leave it on my calculator. Y of 2 is what I'm looking for. Y of 0 is -3, so I get a minus 3, so plus 3. And then I'm going to subtract 3 on both sides. So go to the calculator, -3. I don't think this will go to a fraction. I'm pretty sure because of the trig it won't, but I'm going to check. Nope. So my position is 56/3, or you could write it as 18.3.666, and 1.286. The reason they put this on FRQs is they're long, and I could actually ask to do the X piece, the Y piece, and get many points, or part A could be the X and part B could be the Y. So because of that, because these are so lengthy, that's why you normally see these more as a free response than a multiple choice. But that's another way to use integration with parametric functions.